Okay, so let's dive right in. We're always hearing about new AI models, right? But the real revolution, the magic, is happening behind the scenes in how we actually build them. Today, we're looking at a huge breakthrough from Meta that could make that entire process 10 times faster.
Think about it. Every single day, whether you're asking an AI for a recipe or to debug some code or maybe translate a sentence, you're talking to a massive model that had to be taught how to do all that. So, how does that happen? How do we teach it to get things right? Well, I'll tell you, it is not magic. It's this super intense and honestly, until now, incredibly slow process of training and fine-tuning. And that process, it has a massive bottleneck.
Okay, so before we get to the solution, we gotta really dig into the problem first. Because when you're training AI at the scale of something like Llama, well, the problems are just as massive.
A huge part of this training is something called reinforcement learning, or RL. You can basically think of it like a feedback loop. The AI tries something and we tell it, hey, that was good, or nope, that was bad, and it learns. This is exactly how we make these models more helpful, less likely to just make stuff up, and, generally safer for us to use.
But trying to do this at a massive scale? It's a total nightmare. I mean, you're juggling these incredibly complex algorithms across thousands of powerful, really expensive computer chips, GPUs, and any little inefficiency creates what the engineers call idle bubbles. It's literally what it sounds like, moments where a super powerful GPU is just sitting there, doing nothing, waiting for another part of the system to catch up. And all that waiting, it just burns time, energy, and a whole lot of money.
The best way to picture it is like a massive GPU traffic jam. Imagine thousands of lanes of highway all packed. If just one car in one lane stalls out, what happens? The entire system just grinds to a halt. That's the bottleneck we're talking about. But what if you could just get rid of that traffic jam? What if every car could just, teleport to its destination? That's kind of the wild idea behind Meta's new solution, LlamaRL.
And here it is. This is the research paper where they lay it all out. LlamaRL is a framework built for one purpose, to smash through that training bottleneck for these giant models.
Okay, the key word you need to grab from this quote is asynchronous. That right there, that's the secret sauce. So let's break down what that actually means, because it changes everything.
Right, this is the big one. This is the fundamental shift in thinking that makes LlamaRL so incredibly powerful. It's all about changing the entire workflow from being sequential to being parallel.
So, the old way, that's synchronous training. It's like a really strict old-school assembly line. Step 1 has to finish completely before Step 2 can even think about starting. If Step 1 gets delayed for any reason, well, everyone just stands around waiting. But LlamaRL's asynchronous approach? It's more like a modern workshop. You've got different specialists all working on their own parts at the same time in parallel. The pieces just come together as they get finished. No more waiting.
And this diagram from the paper just shows it so perfectly. This is the old synchronous way. See that? You have the generator on one side, creating the training data, and the trainer on the other, learning from it. But look, they work in this rigid one after the other sequence. The generator works, then it stops. Then the trainer works, and it stops. All that gray space in between, that is pure wasted time.
And bam, this is the LlamaRL difference. Just look at this. The generator and the trainer are running at the same time, in parallel. So while the trainer is busy learning from the last batch of data, the generator is already cranking out the next one. Those idle bubbles, all that wasted gray space we just saw, poof, it's gone. Okay, so how on earth did they actually pull this off? Well, it all comes down to a few really clever engineering decisions. So here's how it all fits together. First, they do this really smart thing where they separate the models onto different sets of GPUs. This is huge because it frees up a ton of precious memory. Second, and this is the core principle we've been talking about, they run the processes asynchronously, in parallel. And third, they use this cool technique called direct memory access that lets them update the model's knowledge, its weights, almost instantly. This means every part of the system is always working with the very latest information without ever having to stop and ask for an update. This high-level view just shows how elegant the whole system is. You've got a generator executor and a trainer executor, and each one is just doing its own job. Sure, they talk to each other through these dedicated channels, but, and this is the key, they don't wait for each other. They just work.
Okay, the theory is fantastic, right? But does it actually work in the real world? Well, the results are pretty staggering. And here it is, the headline number.
In their tests, LlamaRL was up to 10.7 times faster than the traditional method. And let's be super clear here. That's not a 10 times percent improvement. We're talking a monumental, game-changing leap in efficiency. So let's put that into terms we can actually wrap our heads around. For a massive 405 billion parameter model, the old system took almost 636 hours. That is nearly a month of nonstop compute time. LlamaRL? It did the exact same job in under 60 hours. What used to take almost a full month now takes a weekend. Just think about that.
And here's the real kicker. All of this incredible speed doesn't come at the cost of quality. Not at all. This graph shows the performance of LlamaRL versus the old baseline. They're practically identical. So you get all that speed, a 10x speed up, without sacrificing even a tiny bit of the final model's quality.
Like a 10-fold speed increase isn't just some nice engineering win. This fundamentally changes the entire game for AI development.
Think about the big picture here. When you can test a new idea in just 2 days instead of a whole month, you can innovate so much faster. It suddenly makes it practical to build even larger, more powerful models than before, and it dramatically reduces the cost and the energy needed for training, which, let's be honest, is a huge barrier right now. Ultimately, this kind of efficiency makes cutting-edge AI way more accessible, and that just speeds up the pace of discovery for everyone.
And that really leaves us with this final big thought. We've just watched one of the biggest roadblocks in AI development get completely bulldozed. So now that we can teach our most powerful tools at a speed that we could have only dreamed of just a year ago, the real question is, what new problems are we going to solve tomorrow?